in the unit circle, which we are going to explore today. So let's talk about these patterns. All right, so our special angles, right, are the 30-degree, 60-degree, and the 45-degree angles, right? These come from our special right triangles, 30, 60, 90, and then the 45 degrees. So we don't talk about the 90 degrees really here, but we are going to talk about the equivalence of the 30 degrees, the 60 degrees, and the 45 degrees. So let's talk about the 30 degrees for a minute, right? Okay, everything is based on pi, which is half a circle, which is 180 degrees, yes? So what should you do to 180? What should you divide that by to get 30? 6, okay? So to get 30, we divide 180 divided by 6, which means it's pi divided by 6. Do you see that? 180 divided by what will give you 60? 3. So that's pi over 3. 180 divided by 4 is 45, so that's pi over 4. And these are the special angles in radian, 30, 60, and 45 degrees. Let's focus on the 30-degree equivalent, which is pi over 6. Okay, so pi over 6, if you draw it here, right, that's what it looks like. It's 30 degrees away from the x-axis, right? So now, how do we find all the angles around the unit circle that correspond to 30 degrees away from the x-axis, right? So what you do is, you start with pi over 6. Now the coefficient to that is 1. 1 pi over 6. And what you do is you keep adding 1 to the coefficient. So you go from 1 pi over 6 to 2 pi over 6, 3 pi over 6, 4 pi over 6, and you see the 2, 3, and 4 pi over 6 will cancel with the 6, and the denominator of 6 will go away, right? So what you want to do for this purpose is only keep the coefficients that don't cancel with the 6 in the denominator so that the 6 in the denominator stays intact. So those are 1 pi over 6, 5 pi over 6. The next one that doesn't cancel is 7 pi over 6, and then 11 pi over 6. And these are the equivalents of the pi over 3 here. So that's an angle of pi over 6. This is 5 pi over 6. 7 pi over 6, and 11 pi over 6. So if I were to, just say these by heart, I go, okay, pi over 6, and then let's say 2, 3, 4, all cancel. 5 pi over 6 doesn't cancel. 6, 7 pi over 6, and then 8 cancels with 6, 9, 10, 11 doesn't, and here. All right, more ways to look at this. 5 pi over 6 is 5/6 of a pi. Do you see how that's just short of a full pi? That's why it's just short of a full pi here. 7 pi over 6 is 7/6 of a pi, a little over a pi, so it's a little past the pi. And then here, 11 pi over 6 is just short of 12 pi over 6, which is 2 pi, so it's just short of that, okay? All right, so let's move on to the pi over 4s. These are the equivalent to the 45 degrees, right? So again, we do the same thing. I have 1 pi over 4. That stays intact with the denominator. 2 pi over 4 will cancel. Do you guys know what I mean when I say it'll cancel? So then the next one that keeps the fraction of the denominator of 4 is 3 pi over 4, 5 pi over 4, and 7 pi over 4. So those are the ones that go here. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. What's the next one? 8 pi over 4, which will be a full circle, so you're already completing the 2 pi. Okay? Yeah.
I heard you say, cancel, but canceling means simplify.
Right, simplify so that like the 4 doesn't stay as a 4. It goes away. Yeah. Right, the 4 changes to it. So you want the ones where in the denominator the 4 stays intact. Okay?
Oh, you don't want it.
You only want a denominator of 4. So you want all the fractions where the denominator stays a 4. Okay.
Basically where the numerator is on.
Huh? Well, only because of the 4, right?
Also for the 6.
Huh?
Also for the 6.
Right, there's 9, right. So it's the ones that don't cancel, that don't have any. Okay, so then the next one is pi over 3. So pi over 3, remember, is 60 degrees away from the x-axis. So it's 1 pi over 3, 2 pi over 3. 3 pi over 3 doesn't work. 4 pi over 3 works. And then 5 pi over 3 is the next one. What's important is in trigonometry, everything is about the x-axis. Every single one of these is 60 degrees away from the x-axis, right? That's what you need to be careful of, all right? Okay. So now let's talk about quadrantal angles. Quadrantal angles are the angles whose terminal side lies on either the x-axis or the y-axis. So we already know this. 0 degrees or 0 radian is the first quadrantal angle. Then 90 degrees or pi over 2. 180 degrees or pi. 270 degrees or 3 pi over 2. And then 360 degrees or 2 pi. So very often, right, let's say we'll talk about an angle of 4 pi over 3, right? So how do you have to know like this where 4 pi over 3 is, at least what quadrant it's in. So in the beginning, I'm always like, okay, 4 pi over 3, right? 1 pi over 3, 2 pi over 3, 4 pi over 3 will be here, right? You just need to do that very, very quickly, all right? So if I tell you where is 7 pi over 6, okay, let's see, 1, 5, 7 pi over 6, 11 pi over 6, okay? All right, questions? Okay. Yep.
So is 7 pi, what's the degree of the angle of 7 pi?
7 pi over 6, which quadrant did we say it was in? The third quadrant. So 7 pi over 6, and that corresponds to the 30 degrees. It's 30 away from 180, so 210.
Oh, okay.
Okay. All right. So here, putting it all together, label the diagram with the special angles. So the degrees over 0 to 360 and the radians from 0 to 2 pi. You know, instead of doing it as independent, why don't we quickly do it together? Let's do all of the degrees, right? So this is 0, and then it's what? 30, 45, 60, 90. And then 120, right? 150, 180. So take a look. It's 30 degrees from here to here, and then 15, 15, 30. So 30, 15, 15, 30, right? So then 30, 15, 15, 30. Okay? 225 and 240. And then I go 30 more, 300, 15, 15, and there are like so many patterns, right? So many patterns. So look, these are the special angles around the triangle. Notice the middle ones are all the ones that end in a 5, right? Because it's 15 away from the 30, right? Okay. And then, right, so then with the radian, you guys can do that, right? So this is pi over 6. Let's just do it quickly. Let's do all the pi over 6s. So pi over 6, what's this one here? 5 pi over 6, and then 7 pi over 6. No, because the pi over 6 corresponds to 30 degrees. That means it's 30 degrees from the x-axis. Okay, what's pi over 6? How many degrees? 30. It's always 30 degrees away from the x-axis, which will go here. That would be 60. So let's do the pi over 3 then. All the pi over 3. And then all of the pi over, I'm going to do all of the pi over 3. So 2 pi over 3, 4 pi over 3, right. So let's do the pi over 4s. 1 pi over 4. Okay, how come it doesn't write? Right. 5 pi over 4. Right. And 7 pi over 4.
That's a 7.
Huh?
That's a 7.
Where? Here?
Yeah.
7, yeah. So look at the coefficients. 1, 3, 5, 7.
Alright, it just looks like this is.
I know. Okay. All right. And then you can do the quadrantal, right? 0, pi over 2, pi, 3 pi over 2, 2 pi. So again, you know, if I tell you, you know, where is 5 pi over 3? You're like, okay, 1 pi over 3, 2 pi over 3, 3 pi over 3 doesn't work, 4 pi over 3, 5 pi over 3. Just go through. Okay. If you, okay, it does take a little practice. Maybe we can do it later. Okay. All right. So we're going to move on to 12.3. We're combining some things. All right. So trig functions of general angles. So suppose you've got some angle, not a special angle, just some at a random point, right? What you know about that random point is its coordinates, okay? So x comma y. Do you see how if you draw a radius to that point, that creates an angle in standard position, right? So now, and you also see how here we have a little right triangle? It's all about the right triangles. So your theta, your angle is always between the x-axis and the terminal side. The x-axis and the terminal side. So here, okay, so if this point is -3 comma -4. Oh my God, why can't? Okay, so if this is -3 comma -4, how much is that y length? How much is that vertical length? So yeah, if this is at -3 comma -4, this has a length of 4 over here. The vertical side has a length of 4, and the horizontal side has a length of 3. How would you find this side, the diagonal? What would you do? Pythagorean theorem, okay? So you do Pythagorean theorem and you find that side r. In this case, it's going to be 5. Now, if this is your angle and you've got the opposite, the adjacent, and the hypotenuse, would you be able to find sine, cosine, tangent? You could. So that's what we're going to do today. Okay, that's what we're going to do right now. So let's take a look at this one actually here. The terminal side of theta in standard position contains the point -3 comma 4. Okay, so why don't we go ahead and draw that? Yeah, the angle. So I'll show you where it is. So first you put the point -3 comma 4. Okay. So here, -3 comma 4. Okay, so then you draw a terminal side, okay, from here to there. So what does the full angle look like along with the initial side? This is the angle, okay? Now, notice when you create that, there is a triangle that's created here. This is the one that you call theta every single time. Why that one? Because it's got to be between the terminal side and that nearest x-axis. So now, this has a side of -3. This has a side of 4. And how do I find this one? The radius, it's 5, Pythagorean theorem. Okay? Now, what we have to do is find sine, cosine, tangent, and all that stuff. So sine of theta, cosine of theta, tangent of theta. So look at sine of theta. It's what over what? 4 over 5. Now, where was our point? Here. Look at that x and y coordinate. Do you see that? Do you see how this is just the y coordinate over 5? So now cosine is going to be negative 3 over 5, which is just the x coordinate over the radius. Tangent is 4 over negative 3, which is just y over x. Okay? So here, sine is y over r, x over r, y over x. And now we can find the other ones. Cosecant is 5 over 4. Secant, negative 5 over 3. Cotangent, negative 3 over 4. Okay? Do you have to draw it every single time? You really don't. If you would like to, fine. Otherwise, what we normally do is, this is x, this is y. Do the Pythagorean theorem with these to get r, and then you can just use it that way. Okay? All right. Let's talk about reference angles. Okay, reference angle is an acute angle. It's formed by the terminal side of, oh, there should be a theta here, of theta. Okay, my computer is slowing down. Okay, let's say theta and the x-axis. All right? So if your angle is in here in the first quadrant, that's the reference angle. If this is your angle here, the reference angle is between the terminal side and the nearest x-axis right here. It always has to be an acute angle, okay, between 0 and 90. So, so suppose you have, let's say, 120 degrees. What would the reference angle theta prime be? We call it theta prime. It would be 60 degrees, right? 180 minus 120 is equal to 60. So I don't ever want you guys to memorize formulas for these. I just want you to reason things out, right? So for example, suppose you have an angle of like 200 degrees. What would the reference angle be? Right, so it is 20 because how do you make an angle of 200? You go 180 degrees, but then from here to here you go 20 more, right? So it'll be 20 degrees. So suppose you have an angle of, 310 degrees. This is 310 degrees. What would that reference angle be? 50 degrees, right? Because you had to go 50 more. Okay, so let's go ahead and find some reference angles here. Sketch the angle and find the reference angle in degrees. So 330 degrees, let's draw that. 330 degrees, that's what it looks like. Theta prime is this one here. This one. How much is it? 30 degrees. Okay. Now, let's do negative 800. Whew, how are we going to draw that? Huh? I know, with the music, right? It's a little bit better over there. Like you hear it more here, but I know. Yep. So let's draw negative 800 degrees. So how are we going to get to, how many times do we have to wrap around here? So if I do 360, how much do I get? So if I do 360 again, so take out your calculators. Let's take out your calculators. So let's do that. So negative 800. So here, whoa. You go. So we just went around 720. Right? How much more do we have? 80 more. So we're gonna go over here. So what would the reference angle be?
No, it'd be 100. It'd be 800.
80. You know?
The nearest one is that.
Yeah. So take a look at what happened. We went 360. Let me do it again. It's so slow today. I don't know why. It's crazy. Okay, so I'm going to start here. All right, so look, I'm going to go downwards, negative 360. Yep. Negative 360 again, I'm at negative 720. How much more am I going to go? 80 more. That 80 more is my reference angle. Do you see that? Huh? Okay. Now, it's so much easier in radian, because in radian, the reference angle is just pi over a, where a is just the denominator of your angle in reduced form, okay? So, suppose you have pi over 3, pi over 6, pi over 4. These are all reduced, right? That's what your reference angle is. So look, 4 pi over 3, reference angle is just pi over 3. 10 pi over 8, is it reduced? It's not reduced. If I reduce it, it'll be 5 pi over 4, so it's just pi over 4. That's how easy it is. Okay? Yeah.
I'm confused why, on the last one, why wouldn't it be, like, why is it 80, like, the past 80, why isn't it just 10?
Because it's between the x-axis and here, not the y. It's always about the x-axis. Okay, so here, let's reduce that. It's negative 5 pi over 6. So what would the reference angle be? Pi over 6. So take a look. Does that even make sense? Let's draw negative 5 pi over 6, okay? This is negative 5/6 of a pi. So I'm going to go just under a full pi. Does it make sense that the remaining here is another 1 pi over 6? Yeah, because I went 5 pi over 6. Another 1 pi over 6 would have been the reference angle. But you don't have to do any of that. You just blindly say pi over 6. Yes.
But why do you just blindly say pi over 6?
Because that's the, well, I just showed you, because because this is dividing pi into sixths. And however much you want, you're just going to go pi over 6 more. Okay?
Oh, so it's
Yeah.
just what you're doing with the remainder.
Yep. Okay, I need to move on. Yeah. Yeah. No, positive pi over 6. So reference angle theta prime is positive pi over 6. It can negative be a negative. Yeah. Theta prime. Prime. We're going to say it so often, you will know.
No, I forgot. I got it.
Okay. Let's sketch this. Okay. 13 pi over 3. This, okay, when I'm drawing angles in radian, this is the only time in my life that I use mixed numbers. Legit, this is the only time that I use mixed numbers. No math teacher likes mixed numbers. We all prefer improper fractions, except here. So what's 13 over 3? It's what in mixed number? 4 and 1/3 of a pi. So let's go ahead and draw that. So here we go. 2 pi, right, 4 pi, and then I'm going to go another 1/3 of a pi, and you can already tell, right, that that's going to be, that the reference angle is pi over 3. But without even drawing it, I ask myself, is 13 over 3 reduced? Yes. So the reference angle is just pi over 3. Okay, that's theta prime. Okay. All right, so here, for each angle, find the corresponding reference angle in degrees or in radian and state the quadrant in which the angle is located. So, 500 degrees. Who says it's going to be located in quadrant 1? Just off the top of your head. Who says quadrant 2? Who says quadrant 3? Who says 4? Okay, let's see. So we're not going to draw it this time. Oops. So 500 minus 360 is how much?